Thank you very much again, and thank you very much to the organizers for this invitation. So I will talk about some identity which actually involves partitions, but appeared from this theory of finite free probability, where actually in the limit typically we have non-crossing partitions. So this was a little bit of a surprise. So I will explain, let me just put this identity. Actually, I tried to look a lot about if this identity was known. And yeah, we struggle a lot in proving this identity, which is like is some cancellation phenomena. So you see, typically we sum over partitions. So this is, but here the blocks are important, size of the blocks, and we take some powers. And it turns out that we know that if you sum over the Möbius function, we get 0. And but it turns out that if you multiply by something for the partitions, as long as n is bigger than m, then this is also 0. And for the case n equals m, so m is just number that depends on the sizes of this, get this exactly. And I will explain why we needed this formula, but I think still this formula is interesting, and if you have a understanding of why it's happening, it will be very nice. But I will give a new proof. This proof is not in the paper. In the paper that sorry, this is joint work with Katsunori Fuji, who is now a postdoc in CIMAT, who was before in Hokkaido, and Yuki Ueda, who is still in Hokkaido. So the proof in the paper was really doing the whole work and calculating a lot of things. Now I have a more conceptual proof using just classical probability. There is no non-crossing partitions. Non-crossing partitions will appear at least in a couple of slides. Yes. If so these B's are the blocks of pi. Yes. Sorry. No. For a pi. Oh, sorry. This is a typo. This k is not the same k. No. Wait. No. This is the same k. K is fixed there. Yes. If k is bigger. No, so this is a polynomial. Yeah, so let me just do the case which is simpler, and we want. Okay, so here we take all of them to be 2. Actually, this is the one which will be more important. And yes, and we want to prove this. Okay, so maybe we come back to this question, and this will be clear at the end of the talk, because probably I will say something wrong. It's the same case. But this will be clear, I hope, at the end of the talk, and I will explain why we came up with this formula. So this comes from this theory of finite free probability, which is somehow a version of free probability which comes from taking matrices which are finite. There was another attempt done from random matrices, but this is a little bit different because now we take characteristic polynomials. Then in 2018, no? We defined, no, maybe a little bit, 2018 is the paper appeared. We defined these finite free cumulants, and recently there was some other applications of finite free probability, and it turns out that these finite free cumulants are like the right tool. Like really, some of the problems there, like in relation with derivatives and so on, the cumulants make the job. But I won't talk about this. But I must say that before, like it was just like some tool, and after some years, I realized that it was very useful. But the problem I want to talk today is about this unitary Hermite polynomial and how this converges to a unitary free Brownian motion. And to prove this, we use this machinery. And at the end, this relation that I mentioned now appears, and then we prove this, and more or less this is the outline of the talk. Let me talk about finite free convolution. So as Philippe mentioned in the first lecture yesterday, there is strong connection between random matrices and free probability, namely that in the limit, you have something called asymptotic freeness. So before, or the classical approach of free probability and random matrices is that if you take traces, actually here I just put one variable, but as Philippe explained, if you have traces of moments, sorry, of monomials, then they converge to the expectations when A and B are free. A new approach or perspective is instead of taking traces, you take just the characteristic polynomial. You take the expected characteristic polynomial, and that means really that you take all of the polynomials and you integrate all the coefficients. This is something different. So, sorry? It's different. There is no contention. They are not exactly that because you are integrating. There is if you have only one matrix, this is the same. If you have many matrices and you integrate, the integration gives different answers. Yes. But the thing is that this elementary polynomials is not linear in the eigenvalues. Because you integrate, they are different. That's why they are different. If there will be some function which is linear with the eigenvalues, the three things will be the same. It is different. If you have symmetric polynomials or homogeneous polynomials, this is different. Yes. Okay, so it's exactly this. What I'm saying is that the finite free additive convolution of two polynomials, you take two matrices which have characteristic polynomial A and B, sorry, P and Q, and then you take the expected characteristic polynomial, and this gives another polynomial. One thing which is not trivial, not obvious at all, is that this gives another polynomial which has real roots if the original ones have real roots. And actually, there is a precise formula. Okay, so this is not hard to calculate, which is something which was studied like 100 years ago by Sego and Walsh, and actually this was proof at that time that this was real root. Okay, so the new thing is that actually this polynomial can be seen as the expected characteristic polynomial. This is what Marcus Spielmann and Srivastava noticed, okay, that characteristic polynomials are related with this convolution. Yes. So there you have only two things, and basically the mean and the variance tells you everything. So you can calculate, but okay. No, but I can tell you a central limit theorem is just a Hermite polynomial, and then you have two roots, which is symmetric. I think when this large is more interesting than two. You can also do the multiplicative convolution, and actually the formula is even simpler. It's just like multiplying the coefficients and take normalization. And also the real root was proved by Sego. And they were interested in this, and that's why they call it finite free, because they were able to prove some relations between the R transform of this. You see, this is the R transform of the free additive convolution, as in Philippe explained, but this is smaller when W is larger than the spectrum in the real line. Something similar for this transform. Sorry? W is real and is bigger outside the spectrum, yes. For large W, real one. Okay? And this was translated in how the roots of this polynomial, and they have very nice application to graphs and similar things I use for the Cadison-Singer problem. For us, it is because it approximates free convolution and multiplicative convolution. They didn't know this, but I guess they expected that. And Marcos gave a proof for the additive one, or at least implicitly. We gave another proof using finite free cumulants. And for the multiplicative, we also gave another proof. To say that also there is some notes by Shirachenko and Gionet where they use concentration of measure to give a. This is also another way to do this, but we can do it combinatorially. Yes, for the moment. So I can explain later about analysis, especially in the S transform. Actually, this is a good question. What is the analytical properties of the R transform? And I know people are working on this. We have a very nice result on S transform. I can explain later. Today, only combinatorics. Yes. So in the combinatorial approach, basically you use cumulants, and cumulants should, like in general, for independence, at least the symmetric ones, not monotone one. You expect the first two always. So somehow that this is a polynomial with, on the first moment with leading order Mn. So this is that you can retrieve the moments from the cumulants. Second one is that homogeneous of degree lambda. And the third one is that this is additive. This is when you talk about univariate cumulants. And you have multivariate cumulants. One is the same, two is multilinear, and three is just vanishing of mixed cumulants. At the moment here, we only have univariate cumulants. So for free, this is the case. For finite free, we have something that depends on the polynomial. So this is a P, sorry. So again, so this term is not so important, but it's better for our calculations. You can change this to be monic, but this is not a. So we want just that the leading coefficient has Mn. Second is that this is also homogeneous of degree n. And this d lambda, you can write it as P of x over lambda, but this basically saying that your roots are multiplied by lambda. And the third one is, of course, we have additivity. Okay, so in our paper, original paper, we define this through the R transform that defined Marcus, but we can also define already from the coefficient. A very explicit one. So these two formulas I will use. So the coefficients can be calculated from these cumulants, but also the cumulants can be calculated directly from the coefficients. So these A's are the coefficients of my polynomials. This is just this formula. This is formula. The point is that we have a formula in terms of partitions, but this also you can also have a moment cumulant formula. Okay, so moment cumulant formula is also so this was our original definition. And maybe please don't look much at this formula, because while this makes the job, there is a nicer formula that actually we put it in the paper and we didn't use. Then in the second paper, when we had multiplicative convolution, we realized that that formula was better. And I don't know what we were thinking, but the point is that with this, we can prove that finite free cumulants satisfy 1, 2, and 3. Okay, so it's clear that they satisfy 1, 2, because you see, you just check where is the end cumulant. Right? Definition is either this or here. No, it was given by Marcus, and we proved the proposition. Yes, so we just take the coefficients of the finite Arc transform, but I don't want to talk about finite Arc transform. So now this is given by, actually by Daniel. This is the first thing I put him. Yes. This was given by Daniel. Yes. Or by this, but okay. 1, 2, and 3 are satisfied. 3 is a little bit more tricky. Actually, one uses the formula for coefficients. Okay. Yeah. Okay. Like Daniel. Ask Daniel the details. Well, okay. This is another formula which is better. Okay. So actually, Drew Armstrong once visited Saarbrücken. Maybe he doesn't remember. Maybe he remembers when we were writing this paper. And so you see this formula here. This polynomial was a little bit bothering us. We worked with this polynomial and we proved that so equal. So sorry, this was like typo. No, the minus is okay. It's on the front. Sorry. Anyway, let's look at this formula here. This guy here, this P, this is P of sigma, and P of sigma has this other formula, and then we can rephrase the formula in this form. This form is better because here we can see the leading order. So you see, to prove this, that the leading order of this is not clear because here we have positive and negative numbers. Here it is clear because the leading order depends on the sizes of the partitions. And if you have this condition here, the largest, so the sum of the blocks of pi and plus the blocks of sigma should be at least, at most, n plus 1. This cancels with this n plus 1. Okay? And then you care about exactly that two partitions to see what happens when d goes to infinity. Okay? So, okay, this is just basically permutation and it's Square's complement, the leading order. Okay? This is Pochhammer symbol, and then you do this to pi is the multiplicative extension, but in this case of the Pochhammer symbol. Yes. It's decreasing. So Pochhammer symbol is either increasing or decreasing. Okay, this is okay, Pauling factorial, sorry. This is Pauling factorial. Okay, good. So this is the formula that we should remember, is that the moments are as a sum of over d, and then the leading term is just basically non-crossing partitions, multiplied by something which cancels because you have more partitions with this property, cycles, but this is exactly that. Okay, so maybe first examples. Maybe Marek doesn't like. What we like is that central limit theorem gives Hermite polynomials. Okay, and this is very simple because basically because of the properties that we imposed or proved for the cumulants, the same proof as in classical probability on free probabilities that the second cumulant goes to 1, and the rest of the cumulants go to 0. We have explicit formula between the cumulants and the coefficients, so we can calculate what is the central limit theorem very simply. And similarly, we can talk about a Poisson distribution. I should say that this doesn't come from a limiting like rare events because this doesn't play a role, but you can ask which is the polynomial which has cumulants which are lambda. This is Laguerre polynomial. The statement is that the central limit theorem, so that if you do convolution, 6D, you make n convolution, you normalize 1 over square root of n, and you get a polynomial which has cumulants 0, 1, 0, 0, 0. And then you get the polynomial the zeros, etc. That's the statement. If this is small, yes. If this large is very close. I will try to convince you. Yes, but it's very different. And you can also talk about Poisson distribution or free Poisson, and you get Laguerre polynomial. Okay. I would say that we have also central, like Berry-Essen. We can quantify the central limit theorem. We got also the same rate, but I must say that the constants go to infinity, so it doesn't prove free. But still, we have the same rate of conversion. So this is the Levy distance of the empirical distributions of this guy and this guy. So it's the distance, basically, is the distance between the roots. The smallest distance between the roots. The roots go to the roots, and the distance is 1 over the square root of n if n is large enough. Constants. Some constants, this constant. So this is that the polynomial is centered and has variance 1. Yeah, the finite cumulants, but it's the same. Yes. So we have some measures here. Maybe this. Okay, so we have now we can, so the nice thing is that we can use cumulants to determine convergence. Okay, so this is a statement that follows from formulas of moment cumulant formulas. The leading term is of exactly non-crossing partitions. So one can recover that the following. So suppose you have a sequence of polynomials where the degree goes to infinity, and you want to see if this converges to a measure. Of course, one way to do it is check the moments. The new thing is that you can take the cumulants, but not the same cumulants. For each d, you take the finite free cumulants of this polynomial. And if this converges to the, so if this, to the free cumulants, mu is not a polynomial, or could be a polynomial, but mu is any measure. And if the free cumulants converge to, so the finite free cumulants convert to the free cumulants, then you have convergence. You have moments and you are determined by moments. So example, so we know that I have just mentioned that the Hermite polynomial has cumulants 0 and 1, which is the limiting distribution, is the free, the random variable who has free cumulants 0 and 1, which is the semicircle distribution. This proves that the roots of the Hermite polynomial, normalized property, they converge to the semicircle distribution. Similarly, the finite free cumulants of this Laguerre polynomial are lambda, so they converge to the Marchenko-Pastur, which is the free Poisson. The empirical roots. So you take the roots, your roots, and then you take the measure which has 1 over n in each of the roots for any polynomial. No, sorry, I don't understand. So Hermite polynomials has roots. You take the empirical distribution on the roots, which is 1 over n in each of the roots. This is a measure. And you ask, where does this go? So this is exactly. Okay, sorry, I will need to go a little bit faster. I have until 45. Okay. Okay, no, 45, I will do 45. Okay, now we can do also multiplicative convolution. So multiplicative convolution, as Philippe, again, did in the morning, this gives this, sorry, this is R. Okay, so this is the P and its Kreyer's complement. Okay, and we found a formula for the cumulants for the multiplicative convolution, and that's where we realized that actually the other formula was better, because this is what we get for the cumulants. Okay, and it's exactly the same as before. It is the Kreyer's complement. So exactly the same as before. The only difference is that instead of having here this, we have another one, the one for tau. This is nicer because this is more symmetric than the previous one. Okay, and again, because of the leading order is just sigma and its Kreyer's complement, when d goes to infinity, the leading order will just be directly this. So the consequence is, this is how we prove that finite free multiplicative convolution converges to free multiplicative convolution. This is saying exactly this. This is exactly the same formula plus something of order 1 over d. By the way, we can also do any multiplicative convolution with many guys, and in the limit, of course, we will get m equal partitions. You do this, you take what is this condition, and then you can see that actually this condition, that's why I asked in the morning about this. All block sizes are m. Yes. Okay, so in the limit you get this, but you see these guys are not the blocks of pi, but of the Kreyer's complement. So I have maybe around 10 minutes to talk about the problem I want to solve. Now we have all the ingredients. So the problem I want to solve, and of course, this in principle is not related with finite field probability, but one cool thing that we can use finite field probability because we have some polynomial which natural infinite field probability, and this is this unitary Hermite polynomial. Okay, so this is exactly this polynomial. This polynomial, and I recommend to read this paper by Kabluchko, who proved exactly what I will prove, but using analytical tools. But also explain why you can call this an Hermite polynomial, like unitary. It satisfies some nice properties as the Hermite one, not only from finite free probability. But for us, it was natural to think that this was because Mirabelli, in his PhD thesis, proved that the multiplicative central limit theorem on the circle for finite give this polynomial. So one should expect that in the limit you get the analog, which is the free unitary normal. Okay? So for us, maybe this is just a definition, but it has a lot motivation why we should. Okay, so now the free unitary normal distribution, and this, yes, this is. Very good question. I don't know, but yeah, should investigate. If there is a natural Gaussian on the circle that gives these polynomials as a, right? I don't know. Yeah, no, but I don't know if yes. I will be lying if I will say you that I know that. Okay, now what about the free unitary normal distribution? This is a measure on the circle, which has this property that it is also some limit. It also comes from as the distribution of free unitary Brownian motion. Okay. So it's natural to ask if there is connection, and there's various ways to describe. One is through the S transform. Another one is through the moments, and I think this was proved by Philip. And the last one is by free cumulants. What we want because we are trying to use cumulants. Okay? So our goal is to prove that the finite free cumulants of this polynomial converges to the free cumulants of this polynomial. And so this was proved, as I mentioned, by Kabluchko using analytic tools. This is the question: can we use finite free cumulants to prove Kabluchko's result? And okay, this is the complicated part. And now you will need to pay attention to the formulas. So, so from the formula for coefficients to cumulants, which was our definition of cumulants, we just plug in these coefficients in that formula, and we want to analyze this. Okay, so this is just plugging in what are the coefficients. And then, okay, you see, this has two parts, this b squared and this b times d, which cancels with this d. We have sum over the blocks, but the sum of the number of blocks is n. So from this goes to here, and we have this exactly this expression. We want to know how this expression behaves. So we just expand exponential, and we get this formula. And you see here, the important thing is what is this exponent of d. And if d is larger than k, maybe that's the k. The answer, what is the k? So this is that. So the d to the k, when k is bigger than n, bigger or equal than n, will go to 0 because it's multiplied by d to the n minus 1. So we only care about the first n minus 1 terms. And our goal is to see that this whole thing goes to the cumulants. So we want exactly this. You see, this d is to the k, and k is smaller, so this goes to infinity, unless this is 0. So it should be 0 for k from 1 to n minus 2, and should be exactly this guy for n equals k plus 1. So this is the question that we try to solve. And okay, there was another similar, you can do similar things when you study actually another very nice paper of Kabluchko, where he also proved using sample point, which relates trigonometric polynomials and derivatives of trigonometric polynomials to actually unitary Laguerre. So, and it shows that it converges to the unitary free Poisson. What I'm saying is that there was more general result, and for that other result, we needed this more general formula, not only with the m's equals 2. Of course, we first proved the other one, and then we were motivated to do this one. And I will give you a proof which is using Poisson variables, which is, I think, very nice. This is the idea. So our goal is to prove that this formula. And the idea is as follows. So you put some cumulants which are formal depending on t, which are exactly given by this. So this moment is 1. The zero moment is of course 1, the probability measure. The first moment is 1, and the nth moment is this. This is all formal. I don't claim that this is a real probability measure. Then you calculate the cumulants with respect to these moments. This is exactly this, and you get this. And then you get, to get the formula that you want to derive, if you take the derivative of this and evaluate at 0, you get sum over the squares, and if you derive more times, you get sum of the squares to the k. Okay? So basically what we want to show is that this function has first derivatives which are 0, and then at n equals k plus 1, you get exactly this guy. Okay? And how to do this? So this is the trick. So we consider now the generating function of the generating series of the moments. And to get because this is the moment cumulant formula, so you want the cumulants of this guy. Sorry to be switching. You want the derivative k times of this moment of the log, which is the cumulant, and then you expand this and you get exactly what you want. And we struggle a lot in proving that this is what you want and how to manage. So, but this was this idea that you can use Poisson variables. Okay, why Poisson variables? You see, because Poisson variables have, you can calculate explicitly what is the probability to be I. Okay, and maybe the intuition of why is this true, I can explain later. But okay, the idea is very simple. You take y to be x squared, and then you take the characteristic function of the Fourier transform of this guy, and you see you get this. And then you take the logarithm of this guy. This is the cumulant, so this lambda goes here. So then, by definition of classical cumulants, these are just the cumulants of this variable. Okay? So the cumulants are exactly a polynomial, sorry, the cumulant with respect to k of this variable is exactly what you want. Because you are taking logs of your so the point is that this function here is exactly this function. Okay, so when you modulo this guy, so when you take log and then take derivatives, you get exactly what you want. In summary, what we just say is that what we want to show is, or what we want to know is what are the coefficients of the cumulants of y squared, the x squared. So this is exactly. So what I'm saying is that the numbers that we are interested in is just the end coefficient of ck with respect to lambda. Okay, so but we know how to calculate cumulants of products of variables, in particular x squared. This is the so-called the formula of Leonor and Shiryaev. So it says that if you have a variable which is multiplication of various variables, basically you use sum over all partitions, and you just have this join, where this is just the partition that has 1 to k1, then k1 plus 1 to k2, and so on. In our case, we have just a partition which is of this form. And we want to know first what is the coefficient here. And one thing which is very simple, and that's why I think this is a nice proof, is that if the sizes of the blocks are bigger than k plus 1, then this is 0. Because you need to join, if you have many blocks, then you cannot join things. Because having much blocks gives less way to connect, and the minimum that you need is exactly k plus 1. Sorry, the maximum that you need is k plus 1. Okay, and then one is led to this combinatorial problem, and actually in the appendix of the archive version of this, we give a very nice proof of this fact, really combinatorial proof, with trees. And in the general case, we can prove it immediately. I said 45, so I'll take 2 minutes. So the general case is exactly the same. The only difference is that you need to take multivariate moments, and yeah, it's exactly the same idea. And what you get at the end, no, sorry. What you get at the end is you need to calculate the joint cumulants of powers of Poisson variables. So this trick, which seems very naive, actually saves us a lot. Will have saved us a lot of pages if we have been able to pull the whole thing in the original paper. So let me just finish by asking one small question, is what happens if you put non-crossing partitions? Since you're the experts, maybe you can tell me if there is some similar relation where you sum over Mobius function and you put some powers, and either you get 0 or some quantity when n equals 2. And I don't know how to do this because I don't know, this trick that I did with the Poisson is not, I don't know how to do it. So thank you very much.